Well, for anyone watching on the webcast, we are going to start. I'm Tanner Thompson. I'm a graduate of the BYU Applied and Computational Math emphasis program. I just graduated in August, and I'm going to be talking today about data visualization in Pandas and in Matplotlib. A little bit more background about me. I am a software engineer at Lucid Software in South Jordan, and I'm married to my wife, Sydney, who is actually going to do the second half of this presentation. So without further ado, I think that we will get started with some Python. Oh yeah, Jim's got an announcement.
I'll just stand behind your shoulder, that's fine. I think people can hear me okay. Hi, my name's Jim. I'm one of the people that started this up. I just wanted to let you know that for anybody watching in the next few days, we're part of Big Data Utah, which is a big group of people that usually meets in Salt Lake City. And make sure you go on Wednesday night. And then also keep your eyes peeled for the Big Data, what do they call it? Intermountain Data Conference? What do they call it this year? Big Mountain Data Conference, probably at U of U or downtown Salt Lake City, coming up later this year. So that's about it. I just wanted to make clear that we're on meetup.com under the Big Data Utah group. And I'm going to hand it back to Tanner. And we're very lucky to have him here today. Thank you.
What's up, Easton? Okay, so today I'm going to be presenting on data visualization in Python using Matplotlib and Pandas. So the first thing that I wanted to talk about is Matplotlib. So Matplotlib is a library that allows Python users to plot things in a similar way to Matlab, hence the name Matplotlib. So the first thing, the very rudimentary example I have here is just plotting a graph of the function y equals x squared. So in Matplotlib, the way that you would plot something is you'd take a series of x values and a series of y values and hand those into this function called plt.plot. So to generate x, I'm going to use the Python range function, which takes a lower bound and an upper bound. Lower bound is inclusive, the upper bound is non-inclusive. So what that does is it generates a list that starts at -10 and it's just integers all the way up to 10. Then I would use a little bit of list comprehension in Python to generate a list of all those values squared and then plot that, and it looks like this. So is anyone not familiar with any of those things that I just explained? You guys all know some Python? All right, cool. So as you can see, that plots this nice parabola that we know as y equals x squared. But because my x points were just integers, you can see that it's a little bit jagged. You know, you can see each point. What it does is it just draws a straight line between each one of the points that I give it. So, you know, if I only give it integers on the x-axis, then it's only going to plot one line, and there'll be a little bit of a sharp angle there. So to improve, there's a trick using the library called NumPy. Is anyone not familiar with NumPy? Good, okay. So NumPy is, you can use the linspace function here, generate, instead of just discrete integers from -10 to 10, you can generate a finer set of points over which we're going to plot. And then once you create this NumPy array using np.linspace, you can use this notation, which is a lot easier than the list comprehension. It's just very natural y equals x squared. And so once you come up with x and y, you can put them into plt.plot, and then we get this. So as you can see, it's not jagged anymore. The resolution on the x values is high enough that you can't tell that it's not just a straight curve, or a curve, an exact curve. So as we continue, I've designed this so that you guys can type along, because I think that the best way to learn code is to write it yourself. So you know, if this is stuff that you covered before, and then obviously you'll be fine. Go ahead. My import statements. Okay, yeah. So first of all, NumPy, I've imported as NP. That's pretty standard. Pandas we'll use here in a sec, and I've imported that as PD. Matplotlib is a, and when you use it to plot, you'll use this subpackage called pyplot, and it's pretty standardly imported as PLT right here. We're also going to use PyDataset, which is, I put out a notice in the Slack group earlier about installing this because it doesn't come default with Anaconda, but it is a Python wrapper around a bunch of data sets that are available in R. So that's really useful. And then I'll use the calendar package, which is native to Python. This statement right here, the %matplotlib inline. Has anyone not used that before? Okay, I think you're familiar with it. But for anyone on the Hangout, that allows you to your plots inline as opposed to popping out a new window to see your plots. So, without further ado, here's another example of how to use pyplot within Matplotlib to plot something. I've generated here a lens between 0 and 4 pi with 200 points, so it's a high resolution, and then take in that and use np.sine, which just takes the trigonometric sines of all of those values, and we get a nice sine wave. Any questions so far? All right. So now we're going to do some real data and not constructed data. And I'll be here in front of the keyboard in case anybody has questions that so that I can demonstrate individual things. So to use this PyData package, I've imported data from PyDataset, and there's all sorts of things that are available within PyDataset. Do you remember all of them? Do you just give it no parameters? Yeah, okay, there it is. So if you just call data without any parameters, you get a list of all the different data sets that are available in PyData. So there's some really common ones, like the iris data set is a very traditional canonical data set used in data science. But here we have like 700 some, I think, data sets. Wow. Yeah, 756. So, you know, some of these are really obscure and come from certain research projects, and some of them are really useful, like toothpaste data. I don't actually know anything about that, but if you want to get more info, though, about a certain data set, like that one was toothpaste, so that's kind of intriguing. I have no clue what it is, but we can see what it is by typing in data at toothpaste, and if we just call that, it'll give us the data set itself. But if we want documentation instead, you can give it the parameter of show doc equals true.
And was that the whole data set, or was that just like a head?
That was the whole data set.
Okay. Cool.
But I don't know anything about it, which is why I pulled up this documentation.
Cool.
So toothpaste data, meta-analysis of studies comparing two different toothpastes. So it's got 9 observations of the following 7 variables. The identifier, number of subjects using toothpaste A. I don't know what DMFS. Anybody know what DMFS is?
No.
Maybe that's.
Let's make something up quick.
Maybe that's some sort of like healthcare or health metric. I don't know, or like tooth health metric. So here's some details. Oh, filled surface dental index. Oh, decayed missing filled surface.
Huh.
So it's a dental index. It's used to measure how healthy your teeth are, I guess. So yeah, we have 7 different variables and 9 observations, right? So that's just one example of data that you can get from the PyDataset. But I've got one pulled up right here that is a little more digestible. So this is the Nottingham Castle data. This is temperature data from the Nottingham Castle in England over a course of 12 years. And right here, if you just call, I've assigned it to this variable ndata. And then if I just call ndata, then it shows me the whole data frame. But if I want some documentation, again, I can get it here. So average, it says average monthly temperatures at Nottingham, 1920 through 1939. for 20 years. And if we look at the data, we can see that each data point is 1/12 of a year ahead of the next one. So this is monthly data. Unfortunately, we don't have the name of the months, but we can derive them pretty easy. We just assume the first one is January, the second one is February, etc. And that might even say that in the documentation, but it might not. Yeah, the documentation here is pretty short. It's adopted from our documentation, as you can see. So anyway, a little pro tip for IPython notebooks: if you have lots of output, like I do here, I have 240 lines of output. So if you want to hide the output, or convert it from all the way exposed to scrolling, and then double click, you can hide it. So that's nice if you ever get like a bunch of output and you want to keep it there but not have to scroll past it every time. So another convenient thing, I think we covered this last time, is you can just use this .head on a Pandas data frame to just see the top 5, the first 5 entries in the data frame. You can also give it an argument, so like head 15 gives you the first 15. So that's pretty useful, just to get an idea of like what's in the data frame without having to pull up, like, I don't know, if you have 100,000 things in your data frame, you don't want to load it all. If you just want to get an idea of what's in, a typical entry in the data frame. So now that we have this data, we're going to plot it. Now, Pandas has a really convenient wrapper around the Matplotlib plot function, and you can just call .plot right here on your data frame. So ndata, again, is a Pandas data frame. I'm going to call .plot, and in order for it to know what to plot, you have to give it the values you want it to use on the x-axis and the values you want to use on the y-axis. So if you can see this right here, this column has the column header of time. The second column is not tem, standing for Nottingham temperature. So if we just pass in time as the x value, not tem as the y value, we get temperature on the y-axis and time on the x-axis. And so you can see that it's cyclical, as you would imagine temperature data to be. It goes up in the summer and down in the winter, and seems to stay between about 35 and 65 degrees Fahrenheit. If we want labels, I believe there's also a way to do labels here. I think we might have to do legend equals true. Oh, there was already a legend there, but it has the name of that column. So we could also, instead of if we wanted to make this a little bit prettier to look at, instead of calling it not tem, I think we could do label equals temperature. Now the label on the legend says temperature instead of not tem. Also, I don't know this off the top of my head, but I'm sure that if we wanted to change these labels on the x-axis, so instead of showing decimal years, we could just show like an integer, which would make more sense instead of like 1927.5. Yeah, question?
Mine showed that 1929.35 and 39.
And you use all the same code? But it might just be a function of how big your plot is. You might have a different screen resolution, and so it has different pixels per inch. Because by default, I think it's a 3 inch by 5 inch plot. If you're using Matplotlib to plot, like I did up here, you can change the size, those arguments are by default in inches. If you call plt.figure before you call plt.plot, you can change the figure size of your plot. But I don't know of a way to do that using Pandas. So, you got pros and cons. If you want, you can plot really easy using Pandas, but you'll have more options if you plot using Matplotlib. So you can probably also tweak the color if we wanted color. Somebody throw out a color.
Blue.
Well, it's already blue.
Red.
Hmm?
Oh, it's already blue, right?
Red?
Make it red, yeah.
Ta-da, it's red. Now, let's say that instead of plotting all of that, as you can see right here, it's really squished, and so it's hard to see the detail at the peaks. So let's say we only wanted to plot the first 6 years. There's this argument, or this attribute here called iloc, which allows you to numerically index the rows in a Pandas data frame, and then use this slicing notation like you would in any Python iterable. So if I want to do the first 6 years, that's 72 months, and each row is a month. So I do ndata.iloc and then slice it from 0 to 72 like this. That gives me the first 6 years, and I've called that first 6 years data. And then that creates a data frame as well. And by calling plot and giving it the right X and Y, I can plot just the first 6 years, as you see here. And then I could do the same, I could mess with it the same way and make it a different color and give it a nicer label. But I just showed you that in the previous one. So let's say at this point, what if we wanted to plot just the Januaries or just the Julys? Now you can use iloc to do that as well. Again, the slicing notation, is anyone not familiar with this slicing notation in Python? Okay, great. So this third argument is the step argument. So if this right here means start at 0, go to the end, and then increment instead of by 1 every time, increment by 12. So that means that assuming that the first one is January, then if we go every 12th one should be every January. So the January data is I'm just taking that big data frame and taking every 12th item out of it, and we'll get all the Januaries. Same thing here for July, but I start at 6 and then step by 12 every time. So I've got January data, I've got July data. If I just call this plot function on the data frame, then I can only plot one thing at a time, as you can see. But I've made July red to contrast with January, and you can see January stays kind of between 35 and 44, whereas July is quite a bit warmer. But in order to get them on the same plot, I'm going to use the pyplot, which comes with Matplotlib, instead of just calling the. So I can do plt.plot, and I need to, again, give it a series of x values, a series of y values, and then any other relevant info. So here, January data. To access just a single column of a data frame, you can use this bracket notation. So January data, I'll pull that up here really quick, just so we have another visual on it. Except I haven't actually run any of this. I'll run that. And then January data, you can look at the first little bit of it. So yeah, you can see the index over here. It starts at 1 and then it goes 1, 13, 25. That's because the index is left over from the previous data frame where it indexed the months sequentially. But now you can see that for each time it's year 0.0, so it's January. So the time column is going to be our x values, the not temp, or the temperature is going to be our y values, and you can see here that I've plotted it using 2 different colors, and you can see convincingly that July is way warmer than January. Now, if you wanted to put all the months on the same plot, then one way you could do it would be to do it like I've done this, but you'd have to type out yourself an individual plt.plot statement for each month. And if there's 12 of those, and maybe you want to type that much, but let's say that instead of plotting 12 things, you want to plot 100 things, at some point you want to just do that programmatically. So that's what I've done here. And I've plotted all the months. As you can see, July is this top one, and unfortunately I had a little bit of a color collision. The 2 oranges are February and December, which are similar temperature-wise, but the darker one looks like it's December. So this really low one, although I can't even tell, the 2 oranges are so similar. If you wanted to, you could tweak that, but I didn't get into that too much. You could define your own color map or grab somebody else's color map and kind of iterate through that. But I'll go through the code here really quick. So first what I did is I defined the figure size so that I can make it big enough that you can see these individual things. If I were to take this out, then it would be really tiny and kind of hard to see. And most of all, the legend just gets in the way. So by including this, I make it a little bit bigger, so there's a little more room to breathe on the diagram. Then I have this for loop, and I just iterate from 0 to 11, and I'll plot the Nottingham data, but grabbing just a certain month. There's the X, there's the Y. And then for label, I use the calendar package. Calendar.monthName is essentially just a dictionary in Python that takes a number from 1 through 12 and returns the name of the month. So that was really nice for plotting the legend here. And so again, I used this label argument to create the legend. And then line width I made a little bit thicker because if you just keep it at 1, you can see the lines are really thin. And that's just a kind of a preference thing. You can make them really thick if you wanted to. And then, you know, that's just a style option, but you know, different.
It's starting to look like modern art at that point.
Yeah. Well, and if I commented this out and made it small, then there you go.
There you go, awesome.
So, yeah, I mean, you'll have different needs for different situations, but the point of this is just to kind of show you how you might visualize this data if all you have is just the data and you want to get some sort of graph.
Quick question.
Yeah, go ahead.
You mentioned when people ask questions, you may want to summarize it because I think people can hear my voice on the video, but the short version is you stay grabbing other people's color maps.
Mm-hmm.
So are there like published color maps that your like graphic designers have made and you're allowed to use, or like, you know, royalty free or public domain? Or
Oh yeah, there's a bunch of color maps that are included with PyPlot, and I think Sydney, are you going to use color maps in your half of the presentation? Yeah,
Cool.
Sydney will cover that.
Awesome.
The question though was about color maps and whether there are built-in color maps, and the answer is yes. So that's kind of basic pandas. I wanted to do a little more advanced pandas wrangling, and this actually, I just pulled up this data set right before I started the presentation. So this will be a little bit of an interactive exercise where we're going to decide what sorts of insights we want from this data. I just grabbed this data. It's census data from 2010 and then 2016 estimates from every county in the nation. So I just downloaded that from census.gov. I found, I don't remember exactly how I found it, but I just found it through some Googling. And I've used the pandas.readcsv method to read it in. And if I use head, you can see here the first 5 lines. They're all from Alabama because I guess this is sorted by state name first and then by county name. As you can see, there's 116 columns, so there's lots and lots of data available here. And if we were to get rid of head and look at the entire thing and scroll to the very bottom, oops, how many counties are there in the nation? 3192. So we got a lot of data here. I'll change this back to head. So we have some of these I don't even know. Region 3, Division 6, State 1, state name, county name. Those two are pretty straightforward, obviously. Census 2010 population, estimate base 2010. I don't know what the difference between those two are. I'm sure that if I could find some metadata about this, it would explain it. But I think we have enough self-explanatory data here that we can get some insights. Go ahead, Neil.
So you said there were 3192 rows?
Yes.
Well, if you visit the state names.
Oh, that's true. So 3142. Do you have a question? Okay.
Plus, in that data set, there's still a couple of other special factors. So it's probably 3,100 or something.
Well, I think each line is either a state or a county.
Yeah, but there's just, if you read through the key or whatever for that data set, there's a couple of counties that are like special cases that don't really represent a county.
Oh, you think so?
Yeah, I'd have to look it up.
Or like Washington, D.C. maybe.
Yeah, that's one example. Or there's special cases where the census didn't quite work right or something. I forget, but I worked with that data set a couple months ago.
Oh, cool.
Yeah.
So that sum 1150 is county. So if you filtered by 50, probably 50.
Yeah, I think you're right. So
Foreigners are state.
what if we did counties data at, let's see. We want to select based on what the sum level is. So
Yeah, because 40 to the states.
counties data at, actually, in Pandas, there's 2 different ways to access a column. You can either do the bracket notation that I was using earlier, or you can do dot notation if your column name doesn't have any spaces in it. So
You can actually see counties data apply with a lambda, but I did this one.
oh, you might be right with that too. Oh, oops, I need.
You have to go like greater than or yeah.
Equally for 50.
Yeah. So if we just did that, then that's just the one column. But yeah, if we did equals 50, then we get just the counties. But what I'm wondering is, if there's anything that's not 40 and not 50.
Or you just do not equal to 50 and not equal to 40?
So here we have all the states. I wonder if the District of Columbia, okay, DC counts as a state then on that level. Yeah.
Just try to do it again.
And yeah, Puerto Rico.
I think it's 1%, right?
After this?
Yeah, and then do counties underscore data dot sum of, and make it not equal.
I think it's just the word and.
Is it?
Oh yeah, sorry. I've been writing JavaScript too long. In Python, it's just and.
Oh, okay. Not equals.
I think the ampersand also does work, yeah.
Yeah, you have to worry.
So yeah.
Just try to
So the thing is, the reason for this, I think, is that this is, if you take this, it's not just a Boolean, it's a Boolean series.
Oh, you have to wrap it in parentheses too.
Oh, he's right. He's right. Yeah, that's what it is actually.
Parentheses,
You have to wrap each.
ampersand,
Why don't you want to
you
wrap
have
that?
the series before then.
That's
Two
how
dots
it's.
and happens.
So you think that just wrapping these will do the trick?
Yeah, I think.
Oh, also
Now
that says
wrap
for.
it Now wrap it at the very front and at the very end.
Oh, like this?
Yeah. No.
No, that's not it. No.
Use the internet.
No,
Yeah,
actually, you
yeah.
haven't right in the first place, because it's one Eric's complaining about a series.
So what we need to do is we need to take two Boolean series and AND them together entry-wise.
You just want 1%. I think that works.
This is-
Oh, what do you know? 0. So everything is 40 or 50.
Yeah, everything's 40, 50. Cool.
Sorry.
Easton comes through. So yeah, anyway, what I'm gonna hand this over to my wife in about 3 minutes here, but what insights should we get? Let's see if we could pull up the 10 most populous counties. How would we do that?
We have to exclude states somehow.
Yeah, so let's say counties only would be counties data where sum level equals 50. What was your thing about apply? Can you do dot apply in the lambda function?
Well, you can kind of say to apply, and then you just do, what is lambda x, is it colon? Or,
Yeah,
and then x in, or how do you do these?
it would be x dot sum lev equals 50. No,
I think you actually do counties data sum lev dot apply, now that I think about it, and then you would get, then your x would be each individual items of sum lev. We used that too then, so go back and do it the other way. I like doing these because these will take advantage of parallel processing if you have multiple processors. And actually still will the other way if you don't change it too much.
so counties data at
So counties data dot sum lev. It's 50, 40, right? 50.
yeah, that should be on the counties. Yep.
And what do you want, the biggest population?
Yeah, let's see if we can get the 10 biggest counties. So counties only, and then we would, yeah, is there, I think there's a sort values.
Do the tab, do the tab right there.
Yeah, we get sort index, sort values. Yeah, so sort the values along either axis. So we would want to sort, I think just by default, we want the default axis. So yeah, by list of names or names to refer to the axis items. Yeah, so I think we just do.
You do that, or I think in the original,
Here.
when you make counties only, I think you could just say counties data dot sum lev or dot name on the outside. What's the actual name? State CTY name, and that way you just get a series instead of the whole data frame. Oh, but then it wouldn't be sortable, right?
And
Yeah.
Okay, right.
So I think that we want to do.
Yeah. Sorry.
We want to specify this by argument right here. And we want it by census 2010 pop, or whatever population. We could use 2016 as well. Pass that in as a string and see what it gives us. Oh yeah, okay, we sorted and we found the least populous counties.
Just reverse sort it, we'll just get that one.
So do you think reverse equals true will work?
No, it's,
No. Ascending equals false.
Cool. Oh, LA, big surprise.
Yeah, LA County, Cook County, that's Chicago. Harris County, is that Dallas?
Is that Dallas? Houston.
Oh, it's Houston. Oh, that makes sense.
Let's see how many.
Maricopa County is Phoenix, I think. San Diego County, obviously. Orange County, just south of LA. Kings County is Brooklyn, right?
Yeah, New York. Yeah, you're right, sorry.
Miami-Dade would be Miami, obviously. Dallas County, pretty straightforward. And then Queens.
Cool. And it's funny, a lot of times people are trying to just get the first element and they do all this complicated stuff and you just do head 1 and get it.
Yeah, so we could do dot head 10.
Yeah, or just head 1. If you're really just looking for the first. Yeah, cool.
And then if we wanted to take just the names of the counties, then we could do this and then say dot county name. And there we go. So, any questions before I turn it over to Sydney? All right. You ready, Sydney?
I'm going to stop you from presenting here.
Okay. And I'll disconnect.
Let me know when you're ready to present today. She's got it back. She's and then let me know when you're ready to present. Is your audio still on here, Dan?
It might be. Here, check.
Yeah, we're just going to take a minute here and switch over. Now we're looking at Tanner. Are you still presenting? Shouldn't be. Oh, are you doing 2 screens? This hour or this minute has been brought to you by Proofpoint. Yeah, let's see. How do you do that? You click on gather windows? I don't know.
Okay, hold on.
How do you do
I'll
a
fix this.
default display scaled? We're just working out some display issues here, so stand by. Yeah, I think it would give you an option for single monitor.
Great, it's working now.
Oh, cool. Okay. So let me know, and I'll put you up on the Hangout.
Okay. Should be working now.
Cool. Oh, there you go. And I'm going to make you presenter now. And then just got to switch you. Yeah. Cool.
Okay, so brief introduction of me. So I'm currently finishing my degree at BYU in Applied and Computational Math, and I am a data science intern at Provo, which is why their logo is up, but it's because I work there. Yeah, and so I'm interested in data science. I play a lot with TensorFlow and machine learning models, and it's a lot of fun. And I like data visualization too. It's a really useful tool. Yeah, so let's get started. Okay, so anybody who is following along with this, just so that you can also make the code work, these are my import statements. Obviously, just making sure that things are plotting inline. I've imported Pandas, NumPy, Matplotlib as PyPlot as PLT, and then this Py data set with the data module set up.
That's a good question. What's
What's the thing again where you're doing the percent sign before Matplotlib? That's a Jupyter Notebook thing, but I forget what that is.
Yeah, so this line here, all it's doing is basically making sure that all of your plots appear inside your notebook as opposed to popping up a new window. So when we're plotting things, that it actually shows up here. I don't have to try and switch windows, and it's also nice if you're trying to share notebooks with people. Then if you have this Matplotlib inline statement in there and you've run it, then anything that you've run in your notebook will stay there, and it'll regenerate when you like pull it back up. And so if you save it and send the notebook to somebody else and they pull it up, all of the things that all the plots and all the figures and images and stuff that you have done will stay there, and the other people will be able to see them too, which is really nice. And so I've been turning in homework with, and that's very important for me to do. So anyways, it's just a useful tool. I just prefer it inline. It's not a preference. Okay, so yeah, let's get started. So we're going to play around with some of the data from this PyDataset package, but we're going to play around with some different data sets. So the first one we're going to use is the Titanic data set. So to start off with, we're just going to load the data. And it's, like Tanner showed, it's just as easy as referencing the name of the data set. So this one is Titanic. So come on. Helps if you load the packages first. Okay, so that's done. And then like Tanner said, we can do, looking at the head, and I want to 10-point it out. So I put that in the argument here. And then looking at the shape, just because it's always good to know how many data points you're working with. We have 1,300 data points approximately in this data set, and there's lots of different Titanic data sets out there. This one is only categorical, so I'll be showing you with this data set some different methods of plotting and visualizing some categorical data. Just some really simple ones, and we'll go into more in-depth, more interesting types of plots later on. So just to start off with, just getting some familiarity with Pandas and the way that it works. So because Titanic only has the categorical data here, sometimes the plotting with Panda gets kind of angry with you if you don't translate that into numbers of some sort, a count or an average or something. So what we're doing here with the class data is we're looking at the distribution of how many people were in each class. And we do that by accessing the class column of this data frame, and then we call this function value counts on it, and I'll just show you what it does. So now we have a new Pandas data frame, or I guess a data series, that has two columns. One is the class, and one is the count of people in that class. So here we can see just numerically there's a lot more people in third class than in second and first class, but it'd be nice to be able to visualize that and make it look a little better. So the first kind of plot that we're going to do is just a normal bar plot. So the way we do that is we call on class data. This is important. So after we've called value counts, which tells Pandas to go ahead and count every time each instance of each type of class occurs and put them in a new series, we're plotting that data. We're not plotting the original data, because all that looks to Pandas is just a series of characters, right? So we're calling plot on the class data, and then this parameter here in this function, this just tells Pandas what kind of plot it is. Obviously, it's called kind. So there's lots of different kinds, and I have the documentation pulled up here. So here's the documentation for Pandas data frame plot, and so these here are the kinds of graphs you can create just with your data frame.plot, and they're really easy. I mean, you saw in this that this is a one-line implementation. Yeah, so this is just a really basic bar plot. Like it doesn't look too bad. It doesn't look great. It's just there, right? So some things that maybe you can make it better. We want to put a title on there, and so we just start experimenting with the different parameters that are in the plot data or excuse me, the plot function, and we kind of build off of there and make our plot better and better. So now we have a title on this. Also, I switched the kind, so now it's a horizontal bar plot. That's what this H does. It's in the list of types. Bar H, the horizontal bar plot.
So could you do a pie as well?
We're getting there.
Oh.
Look, it's a pie. Yeah, and maybe you like pie plots better than you like bar plots. So let me. Okay. So this is just going to plot this as a pie plot, and as you see, like the colors are pretty gross, and it's kind of squished, which looks kind of funky. So we're going to start by fixing the color issue. So this is where we start talking about color maps. So I know that there were a couple questions when we talked earlier about color maps making things look a little bit nicer using non-default colors in PyPlot, because the Pandas plot is built off of PyPlot, so you can kind of make the two interact, and we'll kind of see that happening here.
Can I ask you real quick? So is it by default squishing that down a little bit? Like it's almost misrepresenting the data because it's like trying to be 3D.
Yeah, it is squishing that by default. It's because, like Tanner mentioned, the default figure size is 3 by 4 or something, but it's filling this to the figure size.
Oh, so it's still a two-dimensional representation. It's not actually like trying to lay it back.
It's not trying to do any sort of 3D anything.
Okay, cool. Okay.
It's just trying to fill the figure that
Gotcha.
is default. So
Okay.
yeah, here we'll change the color on this so that maybe it looks a little bit nicer. Come on, buddy. Yeah. Yeah, so now we have a little bit nicer looking pie chart, but it's still squished. So like I said, the Pandas plotting and the Matplotlib plotting can interact in a lot of ways because the Pandas plotting is built off of the Matplotlib plotting. So, when Tanner was doing the Matplotlib plotting, he adjusted his figure size by starting with this, plt.figure fig size equals whatever. So if you put that before any of your plotting, you can adjust the figure size. So here we'll see now it looks nice and square, and it's not misrepresenting the data anymore. And I just chose 4 by 4 because I wanted it to fit on the screen, but you can do bigger ones, right? Like, and it'll size itself accordingly and make it look nice. Yeah, so that's just some really basic, like, one-line implementation, sort of get some visualizations out. And this is for categorical types of data. Now we're going to move on to more numeric data types. So we're going to play with the iris data a little bit. So again, like the Titanic data, we're just going to load this in using iris. And this data, just some background on this. I don't remember the guy's name. Anderson, I think is his last name. He went and collected a bunch of data about irises, the flowers. Petal length, petal width, sepal length, and sepal width. And for those of you who don't know what a sepal is, I will show you. Because it helps to know what you're using data for. So sepals are these little green things on the other side of flowers. That's what they're called. Yeah, so petals, sepals. Great. Okay, so we'll load this in, and then looking at the head. So the reason I showed that to you is because we have 4 different types of data here: sepal length, sepal width, petal width, and then the species that's associated with this particular data point. So I'll show you a couple different things on visualizing this data now. So maybe something that would be useful to know is, like, for a particular length and width, or is how many of these flowers are close together in their length and width, and are there any sort of clustering within the data in the sepal length and sepal width? So here we have this function Hex Bin. So we start with plot like we did before, but instead of doing plot and then calling that as a function, we look at the class, and then within there, there's this hex bin function, and I'll show you what it does. It's pretty cool. So now we have this, and so each of these little hexagons is a little bin of data. And so if the sepal width and sepal, this is sepal length on here. I didn't bother putting these axes things, but you could if you did. Let's see if we do that. Hypothetically, it's not working now, of course. Anyways, moving on. Yeah, so each of these little hexagons represents a bin in which data is being put. So if multiple data points, flowers, fall into the same bin, then it increments the like color counter, and that's what this color bar is on the side here. It's indicating how many of these flowers are falling into that bin. So from this, it's a kind of a really cool way to show that we have a bunch of flowers that kind of fall right on this little line here and right in this little line here, and 9 flowers are falling in this bin, and like 7 or 8 are in that bin. So this is interesting, but maybe we don't quite care as much like how many flowers are clustered together. We care more about, if we're plotting sepal length and sepal width, how long are the petals? So we can also do that with hex bins.
Question.
Yes.
Is there any difference between iris.plot.hexbin and iris.plot and then feeding it in the parameter find equals hexbin?
Maybe not. Let's see.
Just a reminder, like, either if you're going to ask a question there, Tom, like one, or you can just rephrase this question.
Oh, so the question was if this works also if we just do kind equals hexbin, calling this directly on plot instead of doing iris.plot.hexbin. So we're experimenting with that.
Okay.
And it turns out, no.
This is the way I was, and I didn't know that you could do it the way you're.
Yeah, well, I guess it's just a difference in the implementation. You can either use the callable plot or access the sub class, or excuse me, sub, what are they called? Functions, sub functions directly. Yeah, so we'll leave it like that. Also, an important thing here, the grid size, I set it to 15 because of the nature of the data we're looking at. If we leave this off, it defaults to 100, and this is not very informative, right? We have each of these points is indicating 1, maybe 2 data points, which we don't really care about, right? We want to see clustering of the data. We want to know more about the data other than, what does it look like in a scatter plot? Because that's basically what this turns into at this point. So that's what you do. That's why you might want to mess with the grid size. And I chose 15 not for any particular reason. It's because I experimented and I found that worked best. 25 seems a little sparse to me, so 15, looked nice. Yeah. So moving on, like I mentioned before, if you wanted to know, how long the petals were for a particular, sepal length and width, you can also do that with these hex bins. And so I'll show you what this looks like. So now this looks a little bit different, right? And this is now showing some really interesting clustering properties. So here we can see that some of these flowers somewhere are having really, really short petals, and their sepal width is like decently long, but their sepal length is pretty short. So they're wide and short little sepals, and the petals are also very short. So that's kind of an interesting thing. And then we see over here that it's kind of the opposite, that these are shorter thinner and longer sepals, and they have longer petals. So that's kind of interesting. This is starting to move into like what you can do with data visualization and how this is helpful in determining clusters within your data and interesting properties of your data beyond just like pie charts. And so you don't have to present 15 pie charts to communicate one result. You can present a single plot to communicate the things that you were intending to show.
That's cool.
Yeah, I like Hex Bins. Also, another interesting thing with this, you can adjust what function you're using so this C parameter here, this is what's creating that third dimension, the coloring in each of these bins. And so it's important when you have multiple flowers falling in the same bin, we could see that up here that we have multiple data points in the same bin. That's also a problem here, because if you have multiple data points and they have conflicting C values, it doesn't know which one to choose. And so you can specify your reduce C function to take all those data points and collapse them down to just one, so it knows what to plot. So the function I used here was just np.average. So it just takes the average of these data points, but you can also use np.max. And here it doesn't make a big difference. You can see the colors got a little bit darker because now we're using the max instead of the average. But on some data that makes a big difference, and it drastically changes the result that you're trying to communicate, whether you're using the max or the average or the minimum. These kinds of choices are inherent in data visualization and the data visualization process. Making these sorts of decisions about what results you're trying to communicate and how you're going to effectively and truthfully communicate all of these different attributes of your data. So another way we can do this is by parallel coordinate plotting. So notice the syntax here is a little bit different. So we're calling pandas.plotting, which is a subclass, .parallel coordinates. So this is a subclass within the pandas package. We're calling parallel coordinates on it. And then we have to pass as a parameter the data that we want. And then this is how it's grouping by color. So the species is, if we remember in our iris data frame, it's the categorical data. So we just tell it in what way we want it to categorize itself. And we could also here subset our data to only some of the categorical aspects. Like with Tanner's county data that he had, there were, the data frame is huge. Maybe we don't want to have a plot that's 4 feet long to communicate only some of that data. Anyways, so this is what the parallel coordinate plotting looks like, and we can clearly see here. And the reason this is interesting is because now we can kind of see that each of these 3 different species of flower is kind of taking on their own particular shape, right? That Virginica and versicolor are really close, but the versicolor is a little bit damped on everything, right? The sepal length is shorter, the sepal width is less, petal length is shorter, petal width is also a little bit decreased. And then the setosa irises are just completely different. And so now we can kind of start to conclude, maybe these ones were the flowers that are these lighter bins over here. And I guess you guys can't see those super well. Like really faint right over there.
So those are the ones that have a much smaller petal length, much shorter petal length. Yeah, much shorter petal length, and we can see that right down here. This is also a similar way to communicate this data. You could find the same result using this plot here. You would just have to do a little bit of digging. Maybe you'd pick one of these or several of these like bins in here, and you would just query your data and kind of figure out what's up here. What is this?
Do you have a question,
yes.
John?
So on that hex bin, is there something in Matlab that does keys or show the colors or something?
I don't think it's using any kind of machine learning algorithm or anything like that. I think it's just purely like binning it, but in a fancier way.
Yeah, it's not using any sort of fancy machine learning algorithm. It's just plotting it in kind of like a histogram, but in several dimensions. Yeah, a 2D histogram.
I think, John, you're presenting on that next month, aren't you? No, I'm just kidding. I'm trying to get John to do a presentation for us and some financial stuff. We'll see if that happens. And can I just make a quick comment, or it seems like the upshot of all this is that without having to bring in Matplotlib or really set up using the axes and the plot and setting up all these complicated graphs, you just make some really easy calls to a data frame and you have a lot of good-looking graphics that tell you a lot of information.
Yeah, that's the point of using the Pandas implementation of these plotting features rather than using Matplotlib directly. I mean, you have more versatility when you use Matplotlib directly, but obviously you're sacrificing some or your like code succinctness, right?
Well,
I think a lot of times what I see with data scientists is they're not like building an application in Java that's going to get used for years. They're doing one-off things. So you really don't want to spend a ton of time customizing every graph. I mean, you might just analyze this data set once for some medical purpose or something and then move on. At least when I worked at Huntsman, that's what you saw, is they just wrote a script for one-time use and then effectively threw it away. So this is great. And no, we're coming up on 3, but you can go past 3 if you need to. And I think we're planning on doing a Q&A time if people have questions, or obviously go through your presentation, but I'm just saying you don't have to do a hard cutoff at 3 as far as I'm concerned.
Okay, great. Yeah,
if somebody needs to leave early, they're welcome to. But yeah.
Great. Yeah, so just a couple more things. So these are just kind of demonstrating some of the different things you can do with just these really simple plotting techniques. So here you can specify the column sequence. So we essentially just switched the petal and the sepal order in this plot. But now if your pandas columns aren't in a logical order, or the order that you necessarily want, and then you want to readjust them, then that's really easy to do. Yeah, and here are just some of the different color maps. So this one's called winter. Up here with the Titanic, I use one called summer. There's magma. I like that one. Rainbow. That's a little harder to read. Yeah, this is, I really like this website here. It's the Matlab documentation, and it talks about all these built-in color maps. And so instead of having to build your own or specify all these different colors, you can just call a name, which is nice. And I can send this out to the Slack channel afterwards. So just to wrap up, this is a plot that I found online from Randy Olson, and I really liked his plot and his ideas. So this is something that I thought was fun. So he's talking about how less is more, and this is really important in data visualization. So we'll just watch this real quick. So obviously here, this is communicating the exact same information that it was before. But this looks now a lot cleaner, a lot nicer. It's a lot easier to read. There's less going on. It's less cluttery. So I just thought that was a good visualization about visualization, because it's something that I think everybody struggles with at some point, like making sure their plots are clean and direct. Anyway, so we'll just go through this real quick, and this is a really complex example about how you can interact with Pandas data frames and Matplotlib and kind of make it all work together to create something that's really interesting. So we can also tell Pandas to load a data frame from a CSV file, particularly one online. So his data was just online. So we just put in the URL, tell it to read the CSV, and now we have metadata for all these different majors by year. And so, kind of going through here, we can see like he's adjusted these tick marks so they look a little bit nicer. He's taken off the lines on top and bottom so that it's looking a little bit cleaner. And then as we move along through his code, he's adjusting these tick marks a little more, adjusting the exact width and size and where they all appear. This block of code here is adjusting the limits so that it goes only from 1970 to 2010 and only from 0 to 90%. You don't want a bunch of white space hanging off the ends of your graph. It doesn't help anything. You don't necessarily want it. And this is adjusting the size of. this was just, that bit of code was just adjusting the size of these labels. And I'm not intending for people to read all of this code as I'm going through it. I'm just demonstrating, like, this is kind of how you build one of these really complex customized plots, if you wanted to do something more complicated than just like a quick and dirty analysis.
Well, and for people on the Slack channel, you could maybe post this. Would you be willing to post this notebook
I'll
in the
post
Slack
a link
channel?
to his website, and all of the information and plotting stuff is up
that's a
there.
good point.
He has a couple of examples.
Yeah.
I mean, I can also post my IPython notebook. That'll be fine.
Yeah, people like that. Or if you have it in GitHub somewhere in a repo, like post a link to that, or just post the file if you're willing to.
Yeah, that's totally fine. I can do that. But yeah, for right now, I'm not intending people to read this code. It's just, I'm just showing how you kind of build these up. And now he's put these little tick marks across so you can track, you know, with a busy plot where all these percentages are coming across. Now he's just removing the little tick marks because they're unnecessary, because now there's the lines all the way across. You know, just cleaning things up, making it look really nice. And then here he customized the order of, you know, where the majors appear, which isn't necessary. It's something that he chose to do, but it's just demonstrating that you can. And then here is the bulk of the code. So this is basically what it's doing is, here we go, right there. It's just for each one, it's plotting a little time series of how the percentage of people or of women graduating in a particular major has changed over time. And then all of this stuff here is just adjusting the exact position where the label appears at the end of the line, because some of the lines end really close together and so labels are overlapping. So this is the kind of like really detailed stuff that you don't have to worry about if you're not really concerned about presenting this sort of graph. But now we can see, you know, we have all these lines and all of the labels match the color of the line, so it's really easy to read this. You know, this is the difference between like a code that takes a long time to sit down and really construct, and the type of code that, like Tanner presented on the like months data, how you just kind of let it happen. And you know, sometimes the colors are overlapping and it's really difficult to understand what's going on or differentiate between the months. And then this is all just adjusting some labels and making sure that you know, labels are nice, and it saves it to a PNG. So this is, I'll zoom in on this. This is how you would save a figure that you generated, like using IPython notebook or just Python in general. You just call plot.savefig. So that's important for generating plots in sort of setting. But yeah, that's all that I have. Are there any questions? Great.
Well, I was going to say, do we want to actually analyze the social trends we were seeing? No, I'm just kidding. It is interesting to see how like they always point out that there's not, I mean, if you go to a computer science class, you notice there's just not that many women in there. And you can see that in the chart, but then you also see this major growth in engineering. So maybe that's what they're doing, is leaving computer science and going to, you know, real, computer science is fun, but like mechanical engineers and physicists and all those people really impress me. Like, you know, biologists. I mean, I think we have it easy in computer science sometimes because we kind of get to make up our own, you know, abstract structure on the world, right? Whereas people in chemical engineering or petroleum engineering, I can never do that. But no, that's really great. I think you did a great job. Does people have questions? If you do have a question, we're still running a broadcast here on YouTube Live, and people can see it later. So if you have a question and you wanted to get on that, then let me come to you with this microphone. And if not, you know, we could wrap it up and then just talk offline. I think everybody should give her a big round of applause right now. You did a great job.
Thanks.
Are there any questions that want to get online, or should we just wrap up the broadcast and see what people want to do in the lab setting here? Okay, I'm going to cut the broadcast off. Thanks again.